In this video, we're going to work on some practice problems associated with thermochemistry. So let's start with this one. A gas absorbs 2,500 joules of heat energy and expands from 3 liters to 7 liters at a constant pressure of 4 atm. How much work is done by this system? Well, let's get a visual. So let's say we have a flexible container with gas particles inside this container. So this is going to be the system, what's inside of the container. Everything outside of the container is going to be represented by the surroundings. Heat flows from the surroundings into the system. Now we know that heat energy flows from hot to cold. So a lot of thermal energy is going into the system. Anytime heat is absorbed by the system, Q is positive. And this is an endothermic process. That means that the surroundings is losing thermal energy. So the process is exothermic for the surroundings. Now what's going to happen? Whenever you heat a gas is going to expand. And this is indicated by the change in volume. The volume goes from 3 to 7 liters. In order for the gas to expand, it has to exert a force on a container. And this force can be used to do work. It could be used to move a piston or move some type of machinery. Thus, when a gas expands, work is done by the system. If you want to do work on a system, you need to apply a force to compress the gas. But now let's work on this problem. So the gas absorbs 2,500 joules of heat energy. That means that Q is positive. Now we want to calculate how much work is done by the system. And we could use this formula. W is equal to negative P delta V. Now some things you want to know. When let's start with delta V. When delta V is positive, that means that the gas is expanding. As it expands, it can apply a force on an object, and so work can be done by the system. When delta V is positive, W is going to be negative. So W is negative when work is done by the system. As mentioned before, you need to perform work on a system when the gas compresses. The gas will compress if the change in volume is negative. If delta V is negative and this sign is negative, then W is going to be positive. So W is positive anytime work is done on the system. So make sure you understand that convention. When work is done by the system, W is negative. When work is done on a system, W is positive. Now, I want to make sure you understand the concept, so I'm going to summarize it with a picture. So let's have 2 cylinders containing gas inside of it. And here are the gas particles in each cylinder. So remember, when a gas expands, it can apply a force on an object and it can do work. So thus delta V is positive during gas expansion. And so because the system can do work, or work is done by the system, W is going to be negative during gas expansion. Now, during compression, you need to do work on a system. The only way the gas is going to compress is if you apply a force and you make it compress. In that case, the volume is decreasing. And so work is done on a system, thus W is positive. So make sure you understand that. When a gas expands, the volume increases, it can apply a force, work is done by the system. In order to compress the gas, you have to apply a force on it, so you need to do work on the system. Thus, the change in volume is negative and W is positive. So now that we've gotten that out of the way, let's move on to this problem. So as mentioned before, W is equal to negative P delta V. So the volume changes from 3 liters to 7 liters. So the change in volume is the final volume minus the initial volume, 7 minus 3. So that's positive 4 liters. So that's how much the gas expands. And it does so at a constant pressure of 4 atm. You can only use this equation if the pressure is constant. If it's not constant, well, that's going to be beyond the scope of this video. You're going into physics. But we're going to work on this problem as it relates to chemistry. So let's use this formula to calculate how much work is done by the system. So P is 4 atm, delta V is 4 liters. So we're going to get negative 16 liters times atm. Now note that Q is in joules. We want to convert this to joules. So liters times atm is it's a form of energy, or rather a type of unit of energy. And it turns out that 1 liter times 1 atm is equal to 101.3 joules. That's the conversion factor that you need to be familiar with. So W is negative 1620.8 joules. So that's, as you can see, during gas expansion, work is done by the system, W is negative. Now let's calculate the change in the internal energy of the system, part B. Delta E is equal to Q plus W in chemistry. In physics, it's delta E is equal to Q minus W. Now you might be wondering, why the confusion? Well, in chemistry, W is equal to negative P delta V. In physics, W is equal to positive P delta V. So even though these two signs are different, the equations for W are also different for chemistry and physics. So it's kind of like a double reverse, where it works out to be the same. The end result is that for delta E, delta E is still equal to Q minus P delta V. When you combine a negative and a positive, you still get a negative sign. So the end result is still the same, but the way of getting to the final equation is a little bit different. So you want to keep that in mind when dealing with chemistry or physics for this type of topic. So in this example, Q is positive 2500 joules and W is negative 1620.8 joules. Now to illustrate what's happening here, think of the internal energy of the system as the amount of money you have in a bank. The 2500 joules is basically the deposit. Imagine making a deposit of $2,500 into your account. Your account value is going to go up. In the case of this problem, the system receives 2,500 joules of energy, so the energy in the system goes up. However, work is done by the system. Whenever you work out, you're expending energy, you're using up energy. In this case, when the system is doing work, it's using up energy in its stored account, so to speak, or in the system. So this is basically like a withdrawal. And so we have 2,500 joules of heat going into the system, but the system is burning 1620.8 joules of energy by doing work to expand the gas. So now the net change in the energy of the system is going to be the difference between the two. So basically the account value went up by 879.2 joules. So when dealing with the concept of internal energy, think of energy that's flowing into the system and energy that's flowing out of the system. and you have to add or subtract those two values accordingly. So for this example, the system gained a net amount of 879.2 joules of energy. We had more energy coming in than energy going out. Now let's move on to number 2. How much heat energy is absorbed by 70 grams of water if the temperature rises from 25 degrees Celsius to 60 degrees Celsius? Now, anytime we wish to calculate how much heat energy is absorbed by a material, it could be a metal, non-metal, a liquid, a solid, doesn't matter. But if there's a temperature change associated with that object, we could use Q equal MCAT. Q represents the energy absorbed or heat, kind of like what Q represented in the last problem. M is the mass in grams, C is the specific heat capacity, and in this example, the specific heat capacity of water is 4.184 joules per gram per Celsius. So this means that it takes 4.184 joules of heat energy to heat up 1 gram of water by 1 degree Celsius. That's what the specific heat capacity tells us. So it takes water a lot of energy just to raise the temperature by 1 degree Celsius. So this tells you it tells you the ability of a material to store thermal energy relative to its temperature change and relative to its mass. Now let's go ahead and plug in the numbers for this equation. M is 70 grams, C is 4.184, and let's write the units: joules per gram per Celsius. And the change in temperature, 60 minus 25 is 35 degrees Celsius. So the temperature goes up by 35. So note that we can cancel the unit Celsius and the unit grams. So Q, we're going to get it in the unit joules. So it's going to be 70 times 4.184 times 35. And so the answer is 10,250.8 joules. Now we can convert that to kilojoules by dividing this number by 1,000. And so we can say that Q is approximately 10.25 kilojoules. So that's how much heat energy is absorbed by 70 grams of water when the temperature goes from 25 degrees Celsius to 60 degrees Celsius. Now I want to take a minute to make sure that you understand the concept of specific heat capacity and how it relates to the ability of an element to store thermal energy. So here we have two substances, substance A and substance B. Let's say that the specific heat capacity of substance A is 0.1 joules per gram per Celsius. And for substance B, it's 1 joule per gram per Celsius. So the specific heat capacity of substance B is 10 times greater than substance A. Now let's say that the mass of each substance is 1 gram, just to keep things simple. And let's say that the initial temperature of each substance is 20 degrees Celsius. Now let's say we were to add 1 joule of heat energy to each of these two substances. What will be the new temperature? Well, keep in mind what this means. It takes 0.1 joules of thermal energy to heat up 1 gram of substance A by 1 degree Celsius. So if 0.1 joules can raise the temperature by 1 degree Celsius, how much can 1 joule of heat energy raise it by? Well, it's going to raise it by 10 degrees Celsius. So the final temperature for this is going to be 30 degrees Celsius, just by adding 1 joule of heat energy. Now, of course, the mass is very small. If you increase the mass, the temperature fluctuations will be a lot less. Now for this one, it takes 1 joule of heat energy to raise the temperature by 1 degree Celsius if the mass is 1 gram. So we're adding 1 joule, so the temperature is going to go up by 1. So it's going to be 21 degrees Celsius. So notice the difference here. These two substances have the same mass and the same initial temperature, and they're receiving the same amount of thermal energy. The only difference is the specific heat capacity. Substance B can absorb a lot more thermal energy without changing its temperature significantly. Substance A, if it receives a little thermal energy, the temperature jumps up quickly. So substance B is better at storing thermal energy. So if you want a substance that can store heat energy, you're looking for a substance with a very high specific heat capacity. Now, substance A is not good for storing heat energy. However, it is good for transferring heat energy. So this is good as a thermal conductor. Metals are good thermal conductors, and you'll find that metals typically have a relatively low specific heat capacity. Water, on the other hand, has a very high specific heat capacity. And so water is very good at storing thermal energy. So I want to help you to see the differences between these two substances as indicated by their relative specific heat capacity. Now let's move on to number 3. How much heat energy is released when 72 grams of liquid water freezes to ice at 0 degrees Celsius? Now for this type of problem, I recommend using a conversion process as opposed to a formula. Let's start with the amount of substance that we have, 72 grams of H2O. By the way, for those of you who want a formula, Q is equal to N times delta H. In this case, this is being delta H of fusion. Sometimes you could use this formula, Q is equal to M times delta H of fusion. It really depends on the units you have. Sometimes the units could be given to you in terms of joules per gram for delta H of fusion, which you just need to multiply by the grams to get the answer in joules. But in this example, it's in kilojoules per mole. So you need to multiply by the number of moles of substance to get kilojoules in this case. So the formula you use really depends on the units. So thus, since you have to pay attention to the units anyway, it's better just to use a conversion process to get the answer. So let's start with 72 grams of water. And now what we need to do is convert it to moles. So we need the molar mass. Oxygen has an atomic weight of 16, hydrogen is 1, and there's 2 of them. So the molar mass of H2O is approximately 18 grams per mole. So 1 mole of water has an approximate mass of 18 grams. So now that the unit grams cancel, let's convert moles to kilojoules. When 1 mole of water freezes, it's going to release 6 kilojoules of thermal energy. So that's what the heat of fusion tells us. Now, the direction in which the physical changes occur will tell us if energy is released or absorbed. So when liquid water freezes into solid ice, energy is released. Q is negative. However, when solid ice melts into liquid water, heat has to be added. So that's Q is positive because energy is absorbed. So it really depends on the direction of where you're going. If you're going from a solid to a liquid or a liquid to gas, and that's going to determine the sign of the answer. So because energy is released, we're going to add a negative sign. So because Q should be negative anytime heat energy is released. So it's going to be 72 divided by 18, which is 4, times 6. So the answer is going to be negative 24 kilojoules. So that's how much thermal energy is released when 72 grams of liquid water freezes to ice. Number 4, the enthalpy of combustion of propane is negative 2220 kilojoules per mole. How much heat energy in kilojoules will be released if 88 grams of propane reacts completely with oxygen gas? If you want to pause the video and try this problem, feel free to do so. So let's begin by writing a reaction. So we're dealing with the combustion of propane. Propane has the chemical formula C3H8. It's going to react with oxygen gas, and it's going to produce CO2 and H2O. Now let's balance this equation. When balancing a combustion reaction, it's best to balance the carbon atoms first, followed by the hydrogen atoms, and you want to save the oxygen atoms for last because you have O2 as a pure element. You can adjust this number without affecting any other elements. So to balance the carbon atoms, we need to put a 3 in front of CO2. Now to balance the number of hydrogen atoms, we have 8 on the left, 2 on the right. We need to put a 4 in front of H2O. So now notice that we have 6 oxygen atoms in the 3 CO2 molecules. 3 times 2 is 6. And we have 4 in the 4 H2O molecules because 4 times 1 is 4. So we have a total of 10 oxygen atoms on the right side. In order to get 10 on the left, 10 divided by 2 is 5. So we need to put a 5 in front of O2. So now this combustion reaction is balanced. Now let's move our attention to the enthalpy of combustion of propane, which is 2220 kilojoules per mole. Let's think about that. What does that tell us? And that tells us that when 1 mole of propane reacts with excess oxygen, negative 2220 kilojoules of heat energy will be released. Fortunately, we have a 1 in front of C3H8, so we can put the energy associated with this reaction, which will simply be negative 2220 kilojoules. If this number was a 2, this would be twice the amount. It would be negative 4440 kilojoules. But because it's a 1, these two numbers are the same. So make sure you understand that. So the enthalpy of combustion tells us how much heat energy is released when this particular substance, when 1 mole of that particular substance undergoes a combustion reaction. So this is what is known as a thermochemical equation. It relates the amount of thermal energy being released or absorbed with a chemical equation, a corresponding chemical equation. So let's understand this. As we said before, when 1 mole of propane reacts, 2220 kilojoules of heat will be released. Or we could say that when 5 moles of O2 reacts in this reaction, the same amount of heat energy will be released. Or when 3 moles of CO2 is produced, negative 2220 kilojoules of heat will be released. So in this thermochemical equation, we can connect this energy with the moles of any of the 4 substances in this thermochemical equation. So let's put this into practice. Let's work on this problem. So we want to know how much heat energy is released if 88 grams of propane reacts completely with oxygen gas. So that tells us that oxygen is the excess reactant. Propane is the limiting reactant. So we need to focus on the limiting reactant to get the right answer. So we're going to start with 88 grams of propane. What we need to do is convert it to moles. So we have 3 carbon atoms and 8 hydrogen atoms. The atomic weight of carbon is 12.01, and the atomic weight of hydrogen is 1.008. Now I'm going to round it to the nearest whole number, just to keep the math simple. So 3 times 12 plus 8 times 1 is 44. So the molar mass of propane is approximately 44 grams per mole. So we can say that 1 mole of propane equates to a mass of 44 grams. Now our next step is to use the thermochemical equation to convert from moles of propane to kilojoules of energy. So 1 mole of propane will release that amount of energy. So we can cross out those two units. So the answer is going to be 88 divided by 44, which is 2, times 2220. So it's going to be negative 4,440 kilojoules. So that's how much thermal energy will be released when 88 grams of propane reacts completely with oxygen gas. Now let's work on the last problem in this video. The standard heat of formation for methane, CO2, and water are negative 74.9, negative 393.5, and negative 286 kilojoules per mole, respectively. Calculate the standard enthalpy of combustion for methane. In order to do that, we need to write the combustion reaction for methane. With any combustion reaction, the hydrocarbon is going to react with oxygen and is going to produce the products CO2 and water. So like before, we're going to begin by balancing the number of carbon atoms, which is 1 on both sides. Next, we're going to balance the number of hydrogen atoms. So we need to put a 2 in front of water to get 4 hydrogen atoms on both sides. We have 2 oxygen atoms in CO2 and 2 in water. So to get 4 on the left side, we need to put a 2 in front of O2. So now the reaction is balanced. So we need to calculate the energy value associated with this reaction, the enthalpy of combustion. Now to do so with the heat of formation, we could use this formula. By the way, the enthalpy of reaction, well, the enthalpy of this reaction is the same as the enthalpy of combustion for methane, because this is the combustion reaction for methane. Now to calculate the enthalpy of reaction, it's equal to the sum of the heat of formations of the products minus the sum of the heat of formations of the reactants. So the products are CO2 and water, and the reactants are methane and O2. Now we know the heat of formation of CO2. That's going to be negative 393.5. And the unit is kilojoules per mole. For water, it's negative 286. But this is going to be 2 times negative 286 since we have a coefficient of 2 in front of H2O. The standard heat of formation for methane, that's negative 74.9. And for a pure element in its standard state, the standard heat of formation is 0. So now we just got to plug in these numbers. So it's going to be negative 393.5 plus 2 times negative 286, and then plus 74.9. So you should get negative 890.6 kilojoules per mole. So that's the enthalpy of the reaction. And the way the reaction is written is equivalent to the combustion of methane. So this is also equal to the enthalpy change for the combustion of methane. So that's it for this video. So now you know how to calculate the work done by a gas, you know how to calculate the change in the internal energy of the system, you know how to calculate how much heat is absorbed during the temperature change and during the phase change, and you also know how to calculate the enthalpy change of the reaction and how to calculate how much energy is released in the reaction given the enthalpy of combustion. Thanks for watching.